Okay, so the next subtopic that we'll be covering today is the fundamental theorem of arithmetic. Now, what is the fundamental theorem of arithmetic? It says that every positive composite number can be expressed as the product of positive integral powers of prime numbers, and this factorization is unique except for the order in which the factors occur. Now, before getting into this, what exactly is a prime number and composite number? Do you guys know the difference? You have prime and you have a composite. So, any integer would be prime and composite, right? Or is there any number that's not a prime, not a composite? The number 1, for example, is neither prime nor composite. What is the difference between prime and composite? Composite numbers are those numbers which have factors other than 1 and the number itself. Other than the number itself and the number 1, there are more factors. One or more factors are there. Then that number is called a composite number, and a prime number is one which has just two factors. One is the number 1 and the other is the number itself. So any number which has the number 1 and the number itself as a factor, it's called a prime number. If there is any other factor besides these two, then it's called a composite. And what does the fundamental theorem of arithmetic say? It says that any positive composite number can be expressed as the product of positive integral means integers. Integers would be minus 1, minus 2, minus 3, 0, 1, 2, all these are integers. Positive integers would be 1, 2, 3. 0 is not a positive integer. So you have 1, 2, 3, 4, 5, 6. All these are positive integers. Positive integers are also called natural numbers. So you have any positive composite number can be expressed as a product of positive integral powers or natural number powers equal to natural numbers of prime numbers. And what can be said about this factorization is that it will be unique. Unique in the sense that the prime factors would be unique, but the order in which these prime factors are written could be different. What does it mean? For example, take the number 140. When we take the number 40, what we see here, this thing, it's called a factor tree. We'll be taking up how to draw a factor tree in the next illustration that we are going to take. But this is what it is going to look like. So you have a number 140. It is divided into two nodes, child nodes. In the left node, you write the prime factor, and in the right you can write a composite number. Again, you divide this child into two subchilds, and you keep on doing it until you reach a point where both the nodes contain prime numbers. So 7 is a prime number because its factors are just 1 and the number 7 itself. Other than that, there are no factors. So 7 is a prime number. Similar is the case with number 5. It has number 1 and number 5 as factors. There is no other factor besides these two. So 5 is also a prime number. So when both the child nodes turn out to be prime numbers, then you stop. That is where the factor tree is going to end. And in that case, the original number is going to be the product of all the left hand child nodes and the last right node. So 140 will be the product of all these. This is what the factor tree is. So 140 is 2 into 2 into 5 into 7. Again, 140 can also be written as 5 into 28. And the 28 can be split like this. So you have 140 can be written as this. You have 5 into 2 into 7 into 2. Again, 140 can also be split as 7 into 20, and then you go on to the other subchild nodes, and in that case you can write 140 as 7 into 5 into 2 into 2. In all these cases, what you see is 140 has 2, 5 and 7 as factors, and these are multiplied together. Their orders are different. So in one case you write it like this, the other case you write it like this, the third one you write like this, but in each of these cases their products are going to be equal to 140 and the prime factors do not change. So in each case there are two 2's, 1 5 and 1 7. So this is the fundamental theorem of arithmetic. Any composite number can be factorized into prime factors which are unique. So anybody who does the factorization of 140 would get 2, 2, 5 and 7 as the prime factors. But they might get it in different order. So somebody might get it in the form 2 into 2 into 5 into 7. The person sitting next to him can get it in the form 5 into 2 into 7 into 2. And the third person could get it in the form 7 into 5 into 2 into 2. But in all these cases, what you see is that the prime factors, the composition of the prime factors is going to remain the same. Only their orders are going to differ. And this is what the fundamental theorem of arithmetic states, that any composite number can be expressed as a product of positive integral powers of prime numbers such that the factorization is unique but the order may not be. And this is an example by which we showed it. Now let's get into illustrations and then you'll be able to gauge it much better. The question says, is 7 into 11 into 13 plus 11 a composite number? What was a composite number? A composite number can be expressed as the product of positive integral powers of prime numbers. So can we write it as that? Here we see that 11 is common. So take 11 as common, you get 7 into 13 plus a 1 over here. So you have 11 into 7 into 13 is 91 plus 1 is 92. 11 is a prime number, so this is a prime factor, but 92 is a composite number. So we have to prime factorize it. And this you have learned in junior classes as well. How do you do it? You write it as 46. Then here you get 23. Write 23 over here. You get a 1 here. So you have 92 equal to 11 into 2 into 2 into 23, or 11 into 2 square into 7 into 23. So anybody who does this prime factorization, he'll get only these 3 as prime factors with 2 occurring twice. Order could have been different, but this is what you would get. And this is what fundamental theorem of arithmetic states, that any composite number can be expressed as a product of positive integral powers. So what is the integral power here? It is 11 to the power 1 and 23 to the power 1. So a composite number can be written expressed as product of prime numbers and its powers such that they are unique but their orders may be different. So this we have expressed it as a product of prime factors and its powers. So hence we can say that this is a composite number. So it is a composite number is going to be my answer for this particular question. Okay, let's take another question. Here we have to find the missing numbers, and this is what I said is a factor tree. So what did I say? The factor tree is what? In a factor tree, the left node of any parent, a parent has 2 child, and this child again becomes a parent for these 2. Okay, so it says that the left side node of any parent, you are going to fill a prime number. So when you factorize it, the prime factor is going to come in the node on the left. It cannot be a composite number. And the right node is going to have a composite number. So whenever you have, for example, 140 you had, so you first take the first prime factor that you have. So it's divisible by 2. So in the first node, 2 would go in the left node and 70 would go in the right node. Or 140 could also be like 7. So again, 7 is a prime number. So 7 would go in the left node, and in the right node you have 20. But 140, if you take 10 here, then 10 and 14 are not going to come because the left node has to have a prime number. And neither of the two, 10 or 14, are prime. So you cannot have a prime factor tree for 140 such that this is 140 here and you have 10 here and 14 here. And then you go on splitting these two as well. The main rule for a factor tree, this is going to be wrong. Main concern, or the main thing that we have to address in factor tree is that the left node always has to have a prime number. The right node should have a composite number or a prime number when the factor tree ends. Whenever the right node also becomes a prime number and the left is also a prime number, in that case, the factor tree is going to end right there. So each parent node is the product of the numbers in the two child nodes. Each parent is the product of two child nodes, and we have to keep going till both the nodes have prime numbers. This is when the factor tree is going to end. And the product of all prime factors, that is all the numbers that fall in the left node and the last right node, will give you the parent number. In some questions, as in this, the factor tree is not complete. It's a part of a factor tree. You might argue that 165 is a composite number. How have we stopped the factor tree here? The factor tree is not stopped. The factor tree could go on beyond this as well. This is not the complete factor tree. It's just a partial factor tree. So it's okay. So now the rule says that the parent is going to be the product of the two child nodes. So what is going to come in here? In here you have 2 into 165. So you have 2 into 165, which is equal to 330, is going to be filled in this parent node for these two child nodes. And what will come over here? It will be the product of 2 and 330. So 2 into 330 is equal to 660. So you fill in this box as 660 and you complete this partial factor tree over here. Now let's take another factor tree where we have to fill in the missing numbers. So again, let's do it. What do we know? We know that the parent is the product of the two child nodes. So 35 is going to be 7 into y. So what does y come out to be? It comes out to be equal to 5. So in place of y, you can have 5, which is a prime factor. And which is correct because in the left node, you should have a prime number. Now again, 105 is what? 35 into x. So x turns out to be 3. This is very simple. Now, here we don't have the next number. So you have c is equal to 105 into d. So there are two unknowns. So we cannot find out both in using one equation. So we don't find out d in this step. We go to the next parent and child node system. What do you have here? From here you have 630 is equal to 2c. So you get c is equal to 315. So here you were able to find out c is equal to 315. And from this equation c is equal to 105 by d. 105 into d, you get d equal to 3. Because if c is 315, d will be 315 divided by 105, which is equal to 3. Now we go to this step. You have 1260 is equal to b into 630. So b is equal to 2. So you have b is equal to 2. Again here you have a equal to 2 into 1260, which is 2520. So a is 2520. So this is how you fill the entire factor tree. Is this a complete factor tree? Yes, it is, because in the last node, both the child, the left and the right nodes are prime factors. So you can say with certainty that this is a complete factor tree for the number 2520. In this question, this is a partial factor tree for the number 660. This is the way you state it. So this is all about the factor tree. Now, using fundamental theorem of arithmetic, that is by factorizing, the factorization of a composite number into prime factors is what the fundamental theorem of arithmetic is. So using the fundamental theorem of arithmetic, you can find out the HCF and LCM of numbers. Now, what is HCF and what is LCM? HCF is the lowest power of common prime numbers, whereas LCM is the highest power of all the primes. Let's see what that means. When you take HCF and LCM, you have to find out, you first have to prime factorize each of the numbers. So you take 45, you prime factorize. So you get prime factorize means you have to find each of the factors as a prime factor. So you have 45 as 5 into 3, square. The second number is 75. So you have 75, again I can divide it with 5. You have 15, you have 5, 3. You have 5 square into 3. 75 is 5 square into 3. And then you have 125, which you find out is equal to 5 cube. So these are the prime factors for all the three numbers that we have considered. So using fundamental theorem of arithmetic, we have factorized the composite number into its prime factors. HCF, or the highest common factor, is the lowest power of common prime. Which are the common primes in all these three numbers? 5 is a common prime that occurs in all the three numbers. Is 3 a common prime that occurs in all the three numbers? No. 3 occurs in these two numbers, but it doesn't occur in 125. So 3 cannot be considered as a common prime for all the three numbers. So 5 is the only common prime. And what is HCF? It is the lowest power of common prime. So here the lowest power of common prime is 1, because 5 means 5 to the power 1. Here the power is 2, and here the power is 3. So what is the lowest power? The lowest power is 1. So the HCF is going to be 5. And what is LCM? LCM is the highest power of all primes. So here you have 5 and 3 as the prime. Here also you have 5 and 3, you have 5 here. So all the primes we have to consider. It's not about the common primes. All the primes that are there for the numbers, you have to write them down, and then you have to take the highest power of these primes. So what is all primes in these three numbers are 3 and 5. And what is the highest power of these primes? The highest power of 5 is here. So it's 5 to the power 3. And what is the highest power for 3? It's 3 square. So LCM is going to be 5 cube into 3 square, which is 125 into 9. So what does it turn out to be? 1125. So the LCM is going to be 1125. So the least common multiple of the three numbers is going to be 1125, and the highest common factor for these three numbers is going to be 5. And this is the method using prime factorization method, or also by using the fundamental theorem of arithmetic. Let's take the next problem in this section. Another important result that we have to consider here is, for any two numbers A and B, if the HCF is whatever it is, the HCF, the product of its HCF and LCM is equal to the product of the two numbers. This is a very important result, but it is subject to a condition that A and B are not co-primes. I hope you know what co-primes are. Two numbers A and B are said to be co-primes. Two numbers A and B are co-primes if they have no common factor other than 1. So if two numbers A and B have no common factor other than 1, then they are called co-primes. For example, the number 8 and 9. 8 is a composite number, 9 is also a composite number, but in between them the factors are, if you write the prime factors, so the factors are 1 into 2 cube and 3 square into 1. So the only common factor that they have is 1, and besides 1 there is no other common factor. So both these numbers are co-primes. What about 8 and 16? 8 has 2 as a factor, 16 also has 2 as a factor. So these two numbers are not co-primes, but 8 and 9 are. So the condition here is, for any two numbers A and B, the HCF of A and B into LCM of A and B will be equal to A and B if A and B are not co-primes. So in case it is given that A and B are co-primes, then this particular relation is not going to hold. For example, that would mean that the HCF of 8, 9 into LCM of 8, 9 is not going to be equal to 8 into 9. Why? Because 8 and 9 are co-prime. So this particular result is not going to hold. Now, this would also mean that the HCF is a factor of LCM. Using this particular statement that A and B are not co-primes would mean that HCF is a factor of LCM. Please visit this particular concept, and in case you're not able to grasp how exactly I come to this conclusion, we can maybe discuss it in the online doubt class that we'll be having. So you just make a note of this, try to figure out why I write that HCF is a factor of LCM, and only then you can use this particular result. So HCF is going to be a factor of LCM if you are using this result. Now let's see what is stated here. It's given that HCF is of 306 and 657 is 9, and we have to find the LCM of 306 and 657. So the first thing that we need to check is whether A and B are co-primes, which means do they have any divisible? They are not. Hence this particular result is going to hold true, which would mean that 9 into the LCM, which we have to find out, is going to be equal to the product of the two numbers, which is this. So the LCM can be easily found out as 306 divided into 657 divided by 9, which would mean 3 here, 34. So you figure out what 34 into 657 is. So the LCM is going to be 34 into 657. And this is what the answer is going to be. Coming to the next question, it says, check whether 6 to the power n can end with the digit 0, where n is a natural number. Now, for any number to end with a digit 0, what is the unique property that it is going to have? Any number which ends with a 0, you just write it. It will always have 10 as a factor, right? 10 is a composite number. It can always be split into its prime factors 5 and 2. So any number that you take that has 0 in the end is going to have a power of 10 as a factor, which means it will always have 2 and 5 as common factors. So unless and until any number has 2 and 5 both as a common factor, it will never have a 10, and in that case it will never end in a 0. Any number having a 0 in the end should have a 10, right? And for any number to have a 10, the prime factors are going to be 2 and 5. So just to make sure that any number, if you have to check whether it ends in a 0, you just have to check whether the number has both 2 and 5 as factors or not. So we take 6 to the power n. What is 6 to the power n? 6 is 2 into 3. So you can write it like this. So it is 2 to the power n into 3 to the power n. What does the fundamental theorem of arithmetic states? It states that for any number which is 6 to the power n here, any composite number can be written as the product of its positive integral powers of prime factors. So these are prime factors and n is a positive number, so it is of that form. Now what is stated beyond that? It's stated that the prime factors are going to be unique, which means anybody who does this calculation is going to get the same prime factors. So I got the prime factors as 2 and 3. Powers might be different, or the powers would also be the same. When you when you factorize 6 to the power n, you'd get the same power, you'd get the same prime numbers. Their orders might be different. So somebody could get it as 3 to the power n into 2 to the power n. I got 2 to the power n into 3 to the power n. So the order might be different, but the prime factors and their powers are going to be unique, which means that besides 2 and 3, there is going to be no other prime factor for the number 6 to the power n, which means there is not going to be a 5 as a common factor, which means that since you don't have 2 and 5 both as a common factor, which means that 6 to the power n is never going to end in the digit 0. Because although we have 2 as a common factor, there is no 5 here. Okay, and from fundamental theorem of arithmetic we know that the number composite number can be split into its positive integral powers of prime factors, and that factorization is unique. That means nobody can get any other prime factor besides these two. So besides 2 and 3 there cannot be any other prime factor, which means 5 is not there. And if 2 and 5 are both not there, that means the number can never end in a 0. So we can say here that 6 to the power n will not end in a 0. How do you write it? If you want to write it, what will it be? We will say that 6 to the power n can be written as 2 into 3 to the power n, or 2 to the power n into 3 to the power n. Using fundamental theorem of arithmetic, we know that the composite number 6 to the power n can be written as the product of positive integral power of its prime factors, and this factorization is unique. This would mean that 5 is not a factor of 6 to the power n. This brings us to the conclusion that 6 to the power n will not have the number 10 as a factor. So the number 6 to the power n is never going to end with the digit 0. So this is what the method is going to be when you are writing it. And hence you have proved that 6 to the power n cannot end with the digit 0, where n is any natural number. Okay, so the next problem that we are going to consider is again related to the number theory, and we are going to use HCF and LCM and try to solve this question using HCF or LCM, whatever the case may be. Now it says that we have to find the largest positive integer that will divide 398, 436 and 542, leaving behind a remainder of 7, 11 and 15 respectively. Now we have to find some integer, the largest integer. Let this number be q. So what if we state this written statement in the form of mathematical equations? We have to find a number q such that it divides 398 to give a remainder 7. So the divisor is going to be q, the dividend is 398, remainder is 7, the quotient, let it be a. This is what the Euclid's division lemma was, right? What was it? It was dividend equal to divisor into quotient plus remainder. Right, this is what the Euclid's division lemma was. So dividend is 398, you divide it with q, the quotient is a here, we have interchanged it, the quotient is a and the remainder is 7. What happens with the second number? Don't get confused, here q is not quotient, I have just used q as the divisor here. Okay, if you're getting confused you could rename it as d, let's call it d, that will be safer thing to do. So you have 398 as the dividend, d as the divisor, a as the quotient and 7 as the remainder for the number 398. For the second number it's b into d plus 11. The quotient here could be anything, right? It may not be equal to a, so we have written it as b. And for the third number it's 542 is equal to c into d plus 15. This is what is given, and we have to find the value of number d. D is the largest positive integer such that when 398 is divided by it you get 7 as remainder, when 436 is divided by it you get 11 as remainder, and when 542 is divided by it you get 15 as remainder. Now using these three equations, what do you get? From this we know that a into d will be what? 398 minus 7, which is 391. And from this we get b into d is equal to 436 minus 11. 11 goes to the other side, so it will be 425. 5. And from this case, you have C into D is equal to 542 minus 15, which is 527. So these are the three equations I am going to work on. And what am I going to do next? We have to find the value of D. We don't know what A, B, and C are. Now let's use the knowledge that we have gained so far to solve this problem. What is HCF? HCF is the highest, which means highest or largest is same, right? And CF is common factor, right? This is what HCF is. Any number that's the highest common factor of a given set of numbers is going to be the HCF. Now, what can you say about D in these three equations? In these three equations, A, B, C, and D are integers. A into D is 391, B into D is 425, and C into D is 527. So, D is a common factor in all these three equations. So, D is a factor of 391, D is a factor of 425, D is a factor of 527. Factor is any number which when multiplied by any other number gives another number. So D is a factor of 527, D is a factor of 425, and D is a factor of 391. So D is a common factor of 391, 425, and 527. Also, D is the largest positive integer. So it has to be the largest common factor. If D is the largest number and it is a common factor, which means D has to be the largest common factor of which three numbers? 391, 425, and 527. D is a factor of these numbers. It is not a factor of A, B, and C. D is a factor of these three numbers. It also has to be the largest positive integer, hence it has to be the largest common factor, which is the HCF. So what we figured out from the given relations is the HCF. D is the HCF of 391, 425, and 527. How do we solve it? We have done the HCF for two numbers. Now we have got a problem where we have to find the HCF of three numbers. So in such questions, you first take any two numbers, find the HCF, then take that HCF and the third number and you find the HCF, and that will be the common HCF. So first take 391 and 425, use the Euclid's division algorithm. This is one of the methods. So you have 425 is equal to 391 into 1 plus how much do you have? You have 9 here and 25 there. So you have 34 here. The remainder is not 0. So we go to the next step where 391 is equal to 34 into you take it as 111. You have 340, 373 and the remainder 374. So 374 is what you get. So you have 17 as the remainder in this case. Again, it's non-zero. So you have 34 is equal to 17 into 2 plus 0. The remainder comes out to be 0, which means the divisor in this case, which is 17, becomes the HCF of the two numbers 391 and 425. Now what do you do next? You take the HCF of 527 and 17, which is the HCF in the previous case. So you have 527, 17 here. You have 31 and the remainder in the first step itself is 0, which means the divisor, which is 17, becomes the HCF of 527 and 17. Hence D, which is the HCF of these three numbers, will be equal to 17. Okay, so the largest positive integer that will divide 398, 436 and 542, leaving behind the remainder 7, 11 and 15 respectively, is going to be 17. And why we used HCF is because we got these three equations and we figured out that D is a common factor in all these three, and since the question asks us to find the largest positive integer D, hence D becomes the largest common factor of the three numbers 391, 425 and 527. So we basically have to find the HCF of these three numbers. We found it out using the Euclid's division algorithm. We can also find it out using the prime factorization method, and this is something that we should take for this question. We will also try to solve this question using the prime factorization method, finding the HCF using prime factorization method, because that is also something that we took up. And let's see what this will be. So the next step, next method that we discussed is going to be the prime factorization method. And for prime factorization method, again, the equation, till the equation you have to bring the equations, and only then will you be finding the HCF. So what were the three numbers? What were the three equations? These were, so these the common HCF of these three numbers. So 391, when you factorize, what do you get? I know 17, since I know the answer, so I know that 17 would be a factor. You could start with a smaller number. So you have here 2, you have 3 here, so you have 23. You won't be getting a, sorry, you won't be getting a smaller number. So 391 is 17 into 23. 436, 425 is what? 420. You have 5. You have 85 here, you have 5, 17 gives you 1. So you have 425 is equal to 5 into 5 into 17. And the third number is 527. So you have again 17, 31, 1 is what you get. So 527 is 17 into 31. And what did we see in the definition of HCF using prime factorization method? It is the product of common primes, lowest power of common primes. So the primes are 17, 23, 5 and 31. And what are the common primes? The common prime in all these numbers is 17. So you write 17. You write 17 here, and the lowest power of the common prime is 1. So the HCF is going to be 17 to the power 1, which is 17. So the HCF D comes out to be 17. So D, or the largest positive integer that will divide these three numbers, leaving behind the remainder 7, 11 and 15, would be 17. And this is finding out the HCF using prime factorization method. And this the last method that we discussed was by the Euclid's division algorithm method. So this is how you solve such problems. We'll be ending the lecture here today because the concepts were a bit too much to grasp, and so you would probably take some time to revisit these and attempt some questions related to these. And in the second lecture that we will be taking up, we will first be taking up, we'll just recap a few of the concepts by solving a few more questions related to HCF and LCM. And there is an important concept of understanding of representing the HCF as the linear combination of two numbers A and B. So that is something that we'll be taking up. Then we will get into the irrational numbers, and also in the decimal representation of numbers, terminating number, terminating, non-terminating, recurring decimals, and rational numbers. So we will be taking up that, and we'll be ending the concept lectures. The third lecture would be dedicated to your problems. So I hope you got the lecture today, and see you in the next class.